Assalamualaikum and good evening to my beloved lecturer and my fellow friends. Today I will be presenting about our project, which is a support, and my group members are myself, Muhammad Faris, and Muhammad Shazwan, also Walid Nazmi, and Muhammad Ahmad Iskandar. Okay. Okay, for my part, which is introduction. This project focuses on the analysis and evaluation of a titanium alloy component. Specifically TI6AL4V. It's known because of excellent strength to weight ratio and corrosion resistance. For the key analysis method which we employ in the analysis is linear static analysis, thermal stress analysis, and free vibration analysis. For the design criteria include a mass below 0.7 kg, a factor of safety of greater than 2, and a total deformation less than 0.8 mm. The finding will contribute to the development of reliable and efficient design for titanium alloy components in various industries. This project aims to ensure the component can withstand a load of 300 Newton without experience plastic deformation and fracture.
Assalamualaikum and good evening. My name is Muhammad Ahmad Iskandar bin Salahuddin. I will continue for methods. So for methods, we start with design the geometry of projects. Next, we create a material which is aluminium alloy. And then we define the geometry of the project in Ansys and set and create a mesh of 3 mm. And then we set up the linear static analysis and apply the load of 300 Newton. After that, we set the boundary condition and set the fixed support and run the analysis for linear static analysis. After that, we change to thermal stress analysis and set Young modulus to 104 GPa, Poisson's ratio 0.31. And then we set the isotropic instantaneous coefficient to 8.6 times 10 exponent negative 6 Celsius. After that, we change the reference temperature to 25 Celsius. Okay, next we follow the step of linear static analysis. For the continuization methods, we put thermal coordination and select all body. And we change the temperature to 75 Celsius and run the analysis. After we run the analysis, we set up for free vibration analysis and put Young modulus to 104 GPa, Poisson's ratio to 0.31. And then choose create mode shape result and go to tabular data and select all modes. Element size and enter the value 3 mm. And then click method and choose tetrahedrons. And we insert density 4429 kilogram meter cube. And then we run the analysis, collect all of the data, and we got the maximum value of stress and deformation. That's all from me. Thank you.
Okay, for the result of the linear static analysis, we got a max stress of von Mises, which is 53.422 MPa. And the stress location is near fixed surface of the geometry. For the linear static analysis, the max total deformation of the geometry is 0.13894 millimeters and occur at the front of the bracket. Okay. From The data obtained in the analysis, we can calculate the force, which is 16.47. From the data given in the linear static analysis, we got a mass percent difference, which is 11.52, FOS percent difference is 723.5, and the deformation percent difference 82.6. Okay, that's all for me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Wan Al-Nazmi bin Wan Muhammad. For the next slide, I want to talk about result for thermal stress analysis. For equivalent voltmeter stress result, with temperature change, we get 142.27 megapascal, and without temperature change, we get 53.726 megapascal. For total deformation result, with temperature change, we get 0.16 millimeter, and without temperature change, we get 0.14 millimeter. Okay, for the next slide is free vibration analysis result. Free vibration analysis is a method for studying a structure or system natural or inherent vibration when those force or excitation are absent. As we can see from the picture, it's a twisting motion. We get the frequency of 545.6 Hz and total deformation 76.97 millimeter. Okay, for the second total deformation is higher bending modes. It is involve higher order of bending. We get the frequency of 1437.9 Hz and total deformation is 117.4x millimeter. For third total deformation is shear mode. It is involved shearing deformation. We get the frequency of 2492.2 Hz and total deformation is 79.979 millimeter. For the fourth total deformation, it is a combined modes. It is combination of bending, torsion, and shear. The frequency that we get is 3037.9 Hz and total deformation is 306.25 millimeter. For the fifth deformation is a higher order modes. It is involved more complex combination of bending, torsion, and shear. For the frequency, we get 3379 Hz and total deformation is 71.53 millimeter.
As for the discussion, here are the data we gathered for the static structural analysis. We get a lower maximum bond mass stress for the final model, which is here, a greater FOS, and a lower mass by comparing with the first model. And we go for the material selection. We did our research and comparing many kinds of material ranging from aluminum alloy, titanium alloy, and even pure metals. After careful and detailed readings, we reached a conclusion that the best material to go for is titanium alloy with this composition, as it fits all characteristics that we are looking for. The biggest factor that help us to use this material is its amazing weight to strength ratio. Not only it's very durable, it's also very light for the properties it has. So it's just a very nice go-to pick for us. For the thermal stress analysis, these are the factors that contribute to the different results obtained due to temperature effect, which are thermal expansion and contraction, and temperature-dependent material properties. Whilst for the tendency of bracket failure with and without thermal changes, here it is. With temperature changes, the tendency to bracket failure is by the increased stress levels and thermal expansion. And without the temperature changes, it is the material properties and design factors and the mechanical loads. As for the free vibration analysis, here we compare the natural frequency and the force frequency, and we end up with these improvements that we could end up to increase the properties and the structures we brought. This is the improvement we can apply, which is to redesign for increased stiffness, stress concentration mitigation, optimization of bracket supports, and validation through physical testing.
In conclusion, this project studied how a titanium component reacts to temperature changes, handles 300 Newton loads, and vibrates freely. The component showed strength with little deformation and high factor of safety. Temperature changes had a big impact on thrust, so it's important to consider them. The component's natural frequencies and behavior during vibrations were also analyzed. These findings help improve the component's design. To make sure the analysis is accurate, factors like meshing, boundary conditions, measure properties, simplifications, and verification or validation were carefully considered. Adjustments were made to improve the accuracy in identifying the important factors. And hereby, I conclude our presentation. And as the quotes from Steve Jobs, great things are not done by one person, they're done by a team of people. Which I can probably say that's the case for our team. And yeah, thank you.